Hi, I'm Ken Black. Welcome to Business Statistics for Contemporary Decision Making. Today we're going to learn how to construct confidence intervals to estimate a population mean when the standard deviation is known using the z-statistic. Being able to estimate a population mean can be very important for business decision makers. For example, a business researcher might be interested in estimating the mean age of a production worker in the United States. Or perhaps a researcher wants to know the mean number of minutes it takes a commuter to get to work. Or another important area where we need to estimate the mean is estimating the shelf life of a product. For example, what is the average length of life of a battery? Or what is the shelf life of a loaf of bread? Suppose we want to estimate how much, on average, a family of 4 spends on concessions at a Major League Baseball game. We want to be 95% confident of our results, and we know from the past that the population standard deviation is $27. So we set up at a ballpark and we randomly sample 36 different families of 4. So our sample size is 36. We know from past history that the standard deviation of the population is $27. After we interview the 36 families and do computations, it turns out that the sample average of expenditures is $78. In addition to that, we want to be 95% confident of our result. Now, in all confidence intervals, a level of confidence will be given to you as the student. In the real world, we get to select our own level of confidence. Some of the more common levels of confidence are 95%, 99%, 98%, and 90%. So let's take our new confidence interval Z formula and use it on this problem to see if we can estimate the population mean. So rewriting the formula, we have the following. Now, if you note from the numbers that we have here that we've determined that the sample mean is $78. We don't know what the value of Z is yet. We'll look at that in a minute. So we're going to leave that blank. The population standard deviation is $27. Our sample size is 36. And notice in the formula, it calls for the square root of n. So we have the square root of 36. We have the same thing on the right part of the interval. Now it is possible to write the formula merely with a plus or minus value here, but often it is very insightful to write the whole thing out so you can see what the interval looks like. So over here we have plus the same missing Z value times the population standard deviation over the square root of n. So we have the complete confidence interval formula solved for here, except for the Z value. Let's take a minute and learn how to solve for a Z value. So now let's determine how we would figure out what the value of Z is in this particular problem. You might recall from the central limit theorem that sample means are normally distributed for large sample sizes, regardless of the shape of the population, and that the mean of the sample means is the population mean. Now, in this particular example problem, we want to be 95% confident of our results. So we ask ourselves the question, how far would we go out from the mean in this distribution to capture about 95% of the sample means? So if we go out equal distance in each direction, how far would we have to go out in each direction to capture 95% of the values in the normal curve? If we cut the 95% in half and convert it to proportion, we have 0.4750 of the area on either side of the population mean. Now we go to a standard normal Z table to determine what Z value would capture about 95% of the values. Looking at our Z table, you will recall that out in the middle of the Z table are areas, and they are the areas in this particular book from mu out to a given point. So if we look up the 4750 here, go back over here, we get the whole number and the tenths place on the Z value, and at the top we have the hundredths place. As a result, we find that we we get a z of plus or minus 1.96. That is, if we extend out a z of plus 1.96 and a z of minus 1.96 on a normal curve, we will capture 95% of the values. Hence, the z-value associated with a 95% confidence interval is 1.96. Now we can insert our z-value of 1.96 into our equation and come up with our confidence interval to estimate mu in this particular problem. You'll recall that the sample mean is 78, and our z-value is 1.96, and our standard deviation is 27 over the square root of the 36 people or families that we interviewed. Same thing on the right side. That is 78 plus 1.96 times 27 over 36. Now we have all the information that we need to solve for this 95% confidence interval. When we multiply these two together and divide by the square root of 36, which of course is 6, we obtain a value of $8.82. So we can now rewrite our expression with that solved part in it. And from this we can subtract this part and then add this part. And as a result, we get $69.18 is less than or equal to mu is less than or equal to $86.82. And this is our 95% confidence interval to estimate the population mean, or mu. So for our average family of 4 going to a major league ballpark, we can say with 95% confidence that they will spend, on average, the whole population, between $69.18 and $86.82 at a game. This particular portion of the confidence interval has a special name. It's called a point estimate, which to me means this is our estimate in one point in time. If we randomly sample another 36 families, we might get another point estimate. However, this particular part of the confidence interval I refer to as the error of the interval. The error of the interval means that if we were to take into account random sampling and a normal distribution of the curve, because sample means are normally distributed, that we are 95% confident that with our one sample of 36, the actual average expenditure is $78 plus or minus $8.82. Now let's consider what happens when you change the level of confidence in one of these confidence interval estimation problems. Let's write the information that we have from our previous problem along with our 98% confidence level. Our sample mean X bar was $78. Our population standard deviation was $27. And we were sampling 36 families. But now we want to have a 98% level of confidence. How do things change? Well, the level of confidence drives the table z-value. So let's see how it changes. You'll recall that sample means are normally distributed, and the mean of the sample means is mu. And we want to capture 98% of the values. Now, a quick way to look this up in the table is to cut the confidence level in half to 49% and make it 0.49 on each side. That is 4,900 for table purposes, since it goes out 4 values. We look up the 4,900 in the table, and we will obtain a z-value of plus or minus 2.33. Let's put our information together into the confidence interval formula and see what the result is. We have $78 minus the new z-value times the population standard deviation 27 over 36 is less than or equal to mu is less than or equal to $78 plus 2.33 times $27 over the square root of 36. When we compute this part, which we now call error, we get a different value than we got before, and that particular value is 10.485. Now we know this is in dollar bills, and so it may seem a little strange to have the 5 out here, but we're taking the values out until they finish off. So we'll leave that the way it is. We have mu equal $78 plus $10 and 485. Now when we subtract, the result of this is $67 and 515 is less than or equal to mu is less than or equal to $88 and 485. So our 98% confidence interval to estimate mu is this interval. Let's compare it to our 95% confidence interval that we obtained before, which was $69.18, less than or equal to mu is less than or equal to $86.82. So we have a 98% confidence interval and a 95% confidence interval, and the 98% confidence interval is wider than the 95% confidence interval. To summarize, we can estimate population means when the population standard deviation is given using a z-formula that looks like this. In addition, we've learned that most confidence interval formulas are constructed by having a point estimate and an error.